In order to predict shapes or geometry of molecules, we are categorizing molecules into two categories. One, where there are no lone pair of electrons on the central atom. The second category is where we have one or more lone pairs on the central atom. So when you have one or more lone pairs on the central atom, we have so many varieties of molecules. Here E stands for lone pair. E refers to lone pair and A is our central atom. Now before we understand or before we take examples for these cases, we need to understand molecular geometry and electron geometry. Molecular geometry is also referred to as shape. So the shape of the molecule is decided by looking at only the bonded pair of electrons. By observing the arrangement of bonded pair of electrons, you find out the molecular geometry or shape of the molecule. Whereas electron geometry is the shape, we don't refer to it as shape, but electron geometry is decided by looking at both bonded pairs and lone pairs around the central atom. So if you're not considering the lone pairs, then the geometry what you get will be your molecular geometry, and electron geometry is decided by looking at both bonded pair and lone pair. Now one thing we need to remember here is the category of molecules in which there are no lone pairs. If you have molecules with no lone pairs, then molecular geometry and electron geometry will be the same. Since there are no lone pairs, in both cases you will have only bonded pairs. Hence molecular geometry and electron geometry will be the same in molecules where there are no lone pairs. Now since we are studying molecules with lone pairs, we will have molecular geometry as well as electron geometry. Okay, the first one, AB2E. It is as good as having three atoms around the central atom. So it is supposed to be planar, trigonal planar. So if you have three bonded pairs around the central atom, the geometry is trigonal planar. But now we don't have three bonded pairs. Instead, we have a lone pair. So the bond angle in trigonal planar is 120 degrees, whereas in case of sulfur dioxide, there is a lone pair because of which the bonded pair of electrons are pushed away from the lone pair. Lone pair repulsion is more than lone pair bond pair, and bond pair repulsion is least. Now since the repulsion between these two bond pairs is less, they can come closer. So lone pairs are pushing the bond pairs away and the bonded pairs are coming closer, so the bond angle decreases. The bond angle decreases from 120 to 119.5, due to which the shape of this molecule is not trigonal planar. The shape here is bent. It has a bent shape. But if you consider If you consider the lone pair, see, without the lone pair, the shape is like this. It is bent. But with the lone pair, the shape is trigonal planar. So this is our molecular geometry and this is our electron geometry. This is electron geometry because we are considering the bonded pairs as well as the lone pairs. The next one, where we have two lone pairs around the central atom. The simplest example for this is water. Again, in case of water, if we consider only the bonded pairs, the molecular geometry is bent. The molecular geometry is bent because, as I said earlier, lone pair repulsion is maximum. So lone pairs push the bonded pairs away from them, which decreases the bond angle from 120 to 104.5. So the molecular geometry or the shape becomes bent. But the electron geometry, if we are considering all the 4 pairs of electrons there, the geometry becomes like this. If these are the lone pairs and these are the hydrogen atoms, it is somewhat tetrahedral. The geometry of water molecule is somewhat tetrahedral, so we refer to it as distorted tetrahedral. It is distorted because of the presence of two lone pairs. The two lone pairs want to be at maximum distance away from each other, because of which the exact tetrahedral geometry is not achieved. It becomes distorted tetrahedral. So when we are not considering the lone pairs here, both the molecules have same shape, that is bent. When we consider the lone pairs, sulfur dioxide has trigonal planar shape and water molecule has distorted tetrahedral geometry. The next one, where we have one lone pair and 3 bonded pairs around the central atom. Example is ammonia. Now when you look at this image of ammonia, we can clearly see it is tetrahedral in geometry. Of course, I'm talking about electron geometry because I'm considering the lone pair as well. So the geometry is tetrahedral. But when you don't consider the lone pair, it is trigonal pyramidal. So you have the nitrogen atom and the 3 hydrogen atoms. The 3 hydrogen atoms are forming the triangle, and the nitrogen above them forms the pyramid shape. So molecular geometry will be trigonal pyramidal. Next one is where we have 3 bonded pairs around the central atom but 2 lone pairs. Example for this is chlorine trifluoride. Chlorine trifluoride. Now in case of chlorine trifluoride, since there are 2 lone pairs, the electron geometry becomes trigonal bipyramidal. The image clearly depicts it. You have 2 lone pairs in the equatorial positions, one fluorine in the equatorial position and the other 2 fluorines on the axial position. Now the lone pairs in this case need to be in equatorial positions always. They cannot be in the axial positions, because if they are in axial positions, the bond angle here is 90 degrees, because of which there will be more repulsion between the lone pairs and the bonded pair. So in order to avoid that repulsion, the lone pairs will always be between in the equatorial positions, where the lone pair can have a maximum angle of 120 degrees. They can have a maximum angle of 120 degrees. We will talk about this structure in detail in the other video. We need to understand why both lone pairs are not on axial positions and all that. So we will do another video on that. So electron pair is trigonal pyramidal. Electron geometry will be trigonal pyramidal. When you skip these bonded pairs, and if you just look at lone pairs, and if you just look at the bonded pairs, you can see it forms T shape. Chlorine is in the center and we have fluorine atoms, so it forms T shape. So that is your molecular geometry.